So in the previous unit, we only focused on quadratic functions, which I said was a specific type of polynomial function. This section, we are just going to look at polynomials in general and how their graphs usually work. So the first objective, I want to make sure we understand what a polynomial is and what it should look like. And then all of the other objectives, at least 2 through 6, are going to focus on all of the techniques and skills we will need in order to create the graph of a polynomial, and then we will finish with the final objective, actually making the graph. So it looks like a lot of objectives, but you'll see that they kind of all tie in with each other, and it's all building up to this final objective of graphing. So a polynomial function. When I say we have a polynomial, what do I mean? Well, example. This is a polynomial. Let's actually make ourselves a little diagram here. I would maybe write this down. Then we're going to put not polynomials. And I want to see if you can tell me the difference. Something that would not be a polynomial. Something that would be a polynomial. Oh my goodness. Tell you what, this stylus and me do not get along. So that's a polynomial. Something that would not be a polynomial. So how do we put this into math terms? Something that is a polynomial can be written in this form. F of x equals a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus, I could keep going. All this means is if I start with x to the 9th, then I could have x to the 8th, and then x to the 7th. I would keep going all the way down until I get to a sub 1 times x to the 1st plus a sub 0, the term without any x's. The big rule to be a polynomial, the exponents must be whole numbers. And the very first unit we did in this class, I said whole numbers can be 0 on up. So if you see something with negative exponents, like I'll put it down here, 4x to the negative 3, that is not a polynomial. All of the exponents have to be whole numbers. Now, like on this one up here, I don't care that there's fractions as long as they are not the exponent. If you have variables as the exponent, that is not a polynomial. So when we talk about the degree of a polynomial, we're talking about the highest exponent. If we're talking about the leading coefficient, we're talking about the number sitting in front of the variable with the highest exponent. And when polynomials get graphed, they have certain features to them all the time. One big feature of a polynomial graph, it is a continuous graph. There's no breaks in it, there's no jumps in it, it's nice and continuous. Another characteristic, polynomial graphs will have smooth, rounded turns. So I don't want to see any sharp corners or edges. And finally, although I already wrote this up here, exponents are whole numbers. So you should have a picture in your notes of graphs that are polynomials and not polynomials. So notice the ones that are, they're continuous and they have nice smooth turns. The ones that aren't, this first graph, it's not a polynomial because even though it has nice smooth turns, it's not continuous. The next one, even though it's continuous, it has sharp points to it. And those sharp points actually come from a different type of function that's not a polynomial. So when we talk about polynomials, oftentimes we are concerned with what is happening on the ends of the polynomial. Where is it going on the left and where is it going on to the right? That'll also tie into domain. So there's something called the leading coefficient test that can help us figure that out. It's based off of the leading coefficient and the degree of the polynomial. And what this is used for, it's used to describe the end behavior of the polynomial. So what is it doing on the ends? So there are 4 different things that could happen with this polynomial end behavior. What if my highest exponent n is an even number and the leading coefficient is positive? So for example, something like this. Notice my n is even and the leading coefficient is positive. Well, what's going to happen if those 2 things are true, the ends on either side of the graph are both going to go up. Now in the middle, I'm just going to do this. I don't know necessarily what it's going to look like in the middle because it could do this, it could do this, but I know the ends are going up. And that's if the highest exponent is even and the number out front is positive. Well, what if n is even, but the leading coefficient is negative? So something like negative 3x squared plus 2x minus 4. So my highest exponent is even, but the number out front is negative. Well, maybe you already know this, and you should know this from when we talked about parabolas last time. We said if a was negative, the graph opened downward. So I know either side of the graph will be going down. I don't really know what would be in the middle. It depends on what the exponent is. But I know the ends will go down. What if the highest exponent is odd and the number out front is positive? So that would maybe be something like 5x cubed minus 3x squared plus 2x plus 8. That could be an example of something where the highest exponent is odd and the number out front is positive. Well, if you see the word odd, I want you to think opposite. So this means the ends are going to go opposite ways. And since the number out front is positive, I want you to think it's rising from left to right. So the ends are going to do this. The left is going to fall and the right is going to rise. In between, I'm going to draw a squiggle. I don't quite know what it's doing in between, but I know the ends are guaranteed to do that. And the last one, what if the highest exponent is odd and the number out front is negative? So again, I want you to think odd and opposite. That could be something like this. Highest exponent is odd, number out front is negative. So the ends are going to go opposite ways, but this time it's going to fall from left to right. So maybe something like that. So let's try this. Use the leading coefficient test to determine the end behavior of the graphs. So let's identify the highest exponent. So n is even. and the leading coefficient out front, a sub n, is positive. I should now know what the n's are going to do. If it's even, I want you to think the same. They're going the same way, and since it's positive, it's going to open up. So I know they're going to do this. I don't know about the middle, but I know the n's are doing that. So how we would answer this, we would say it rises left and it rises right. Both sides are rising or going up. Now the next one is a dirty trick, and you have to watch out for this. What is the highest exponent? 3. And what is the leading coefficient in front of it? It's a -1. So this one they didn't write in order. If I had written it in standard form, it would have looked like this. So be careful that you are identifying the largest. So since my n is odd and the number out front is negative, odd, I want to think opposite. And since it's negative, I know it's like the graph will be falling from left to right. So we would say it rises on the left and falls on the right side. And now look at the last one. The last one is in a factored form. So we don't want to jump the gun and say, oh, 3 is the largest exponent. You have to think, if I multiplied this all together, what would the leading term look like? So we're going to cheat a little bit. You don't have to FOIL this all together. You're really only concerned with the leader. So if I took this guy times x, that would be 2x to the 4th, and then times the other x, I would get a 2x to the 5th. Really, that's all I need to know. I don't need to multiply the rest out. So my highest exponent is odd, and the number out front, the leading coefficient, is positive. So odd, we want to think opposite. Positive, it's rising, so I know it's going to do this. So we would say it falls on the left, and it rises on the right. So the question is, great, we have the n's figured out, but what about this middle stuff? Because we can't go squiggle, squiggle, squiggle every time for the middle. Well, there is a way to get some more information about what's happening in between the n's. There's something called turning points and zeros. I want us to draw a picture here of a polynomial. So let's say we have our xy axis. And let's say my polynomial did something like this. So when I ask for the zeros, in math, a zero is another term for an x-intercept. And actually, I have a blank down here for it, I guess. A zero is an x-intercept, and you might say, well, why do they call it a zero? Why not call it a 9, an 8? Why is it called that? Well, it's because the x-intercepts, where I cross the x-axis, they are where y is 0. That's why they're called zeros. So this would be a 0, this would be a 0, and this would be a 0. The zeros are the x-intercepts. The turning points are literally where the graph turns around. With the x-intercepts, sometimes they're also called the solutions. So the turning points are where the graph changes direction, or where it turns around. Turning points are easy to spot because they are literally the hills or valleys. They're like the max or min values. So on this graph, there are 2 turning points. There's one here, and there's one here. It's where the graph changes direction. Now, if I'm given a polynomial, there is a way to tell how many zeros I will have. And we've talked about this before in an earlier unit. The number of zeros that a polynomial will have is whatever n is, whatever that highest exponent is. for the degree. So if I have something like x to the fifth, da 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 da, I'm going to expect 5 zeros. The number of turning points will be n minus 1. It'll always be one less than the number of zeros. Because if you think about it, every time I turn around, I could potentially create another zero. So let's try some examples here. State the number of possible zeros and turning points, and then actually find them. So first, let's make sure it's written in standard form. Is it written in decreasing order of the exponents? And it is. So it looks like the largest exponent is a 3. That means I can expect 3 zeros, 3 answers. So then the number of turning points is always one less. I'm going to word it as at most 2, and what I mean by that is it might actually turn around less than 2, but it physically will not turn around more than 2. And now it actually wants me to find these 3 answers. So to find the zeros, and remember that's like the x-intercepts, we're going to put 0 in for y, and we're going to solve for x. So the question is, how do we solve this? Well, we're going to have to factor it, but before we factor, you should notice they have something in common. What can I take out of all 3? An x. So we're going to take a greatest common factor out of x. And now I'm going to factor this guy further. So I want to multiply to 6 and add to -5. What two numbers do that? Should be a -2 and a -3. Don't forget this x out front has to stay there. It just carries down. And once I factored it, I'm going to set each piece equal to 0 and solve. Even the front x. So this front one's done. There's one answer, 0. It looks like I get 3 and 2. There are my 3 answers. So where this would help me with graphing is I know it's going to touch the x-axis at these 3 spots. So that kind of helps clear up the murkiness of the middle part. Let's try another one. So make sure it's in order of decreasing exponent, which it is. So my highest exponent is a 4. So I know there's going to be 4 zeros. So that means at most 3 turning points. And now we're actually going to find the 4 answers. So to find my zeros, which are the x-intercepts, I'm going to set the function equal to 0. And now we're going to solve it. I can take a greatest common factor out of all 3. The biggest thing from all 3 is an x squared. And personal preference of mine, I'm actually going to factor out a -x squared. I think it's easier to factor anytime you can get the leading term, to be positive. So if I divide a -x squared out, I'd have a positive x squared, a plus x, and a -2. Now let's factor further. So I want to multiply to -2 and add to 1. So it would have to be a +2 and a -1. And now I want to set each one equal to 0 and solve. So it looks like I'm going to get 1. It looks like I'm going to get -2. And now this last guy, to solve it, there's like a -1 there. I would divide by the -1, and then I'd have to square root. Now technically, I would get a ±0, which is still 0. So I would have 0 as an answer twice because of the plus minus. So I do have 4 answers. It's just that 2 of the answers are the same number. Now there's a word for that in math, which we're about to touch on next. It's like one of my favorite math words ever. It's called multiplicity. What this is a repeated zero. So like on this previous problem we just did, we would say our answer of 0 has a multiplicity of 2, meaning it was an answer twice. Multiplicity is important to know about, especially if you're graphing polynomials, because it tells me what's going to happen on the graph itself. If a 0 has an even multiplicity, so I get the answer twice, or 4 times, or 6 times, or 8 times, what ends up happening on the graph will touch the x-axis at that spot, but then turn around. If the 0 has an odd multiplicity, so I get it once, or 3 times, or 5 times, or 7 times, what will happen, the graph will cross through the x-axis at that spot. And I'll show you a visual here with this next example of what I mean by that. So find the zeros and state the multiplicity of any repeated zeros. So if I want to find the zeros, I'm going to set my polynomial equal to 0. And then we would try and factor it. But guess what? They already did that work for us. It's already factored. So once it's been factored, I'm going to set each piece equal to 0 and solve. So x equals 0, 2x plus 3 equals 0, and the x minus 1 squared equals 0. Each piece equal to 0. So, well, one answer's done. I have an answer of 0. Next guy, if I subtract 3 and divide by 2, there's my second answer, negative 3 halves. And this last one, if I square root both sides, technically I do get plus minus 0 because I took the square root. So I would have to do 1 plus 0, which is 1, and 1 minus 0, which is 1. So I would get the answer of 1 twice. So what you would tell me, if you were listing your answers, you would say x equals 0, x equals negative 3 halves, and I would prefer you to just say x equals 1 with a multiplicity of 2. So I do have 4 answers. One of them happened twice. So if a shortcut to spot that, up top here, if this would have been x minus 1 to the 5th, you could automatically assume that you would have gotten the answer of 1 5 times. So 1 would have had a multiplicity of 5. What you would see if we were to graph this, although I'm not going to go through the graph, so I had a 0 of 0. I had 1 at like negative 1.5, and then I had 1 over here at 1. What you would happen, or what you would see happen, sorry, since I got negative 3 halves only one time, it has an odd multiplicity, so my graph would cross through it. Since I got the answer of 0 an odd number of times only once, I would cross through it. But since I got the answer of 1 an even number of times, what you would see happen is I'd touch it and turn around. I wouldn't actually cross through it. That's what I meant by the business up above. So this is also helping us figure out what does the middle look like. So we are going to end with, this is that final objective, tying all of this stuff together now and actually creating the graph of a polynomial. So graph this polynomial. Well, there's certain things that I would want you to identify as we go through this process. First, Let's talk about what's happening on the ends, the end behavior. So to do the end behavior, this is where I have to look at the leader, the highest exponent, n is even, and the number out front, which is like a positive 1, is positive. So now I have to think, which of those 4 types, what's going to happen with these ends? Since it's even, we're going to go the same way, and since it's positive, I know the ends are going to be going up. Great. Now we're going to attempt to figure out this middle part. What's it doing in between the ends? So to do that, one thing we're going to identify are the x-intercepts, or also known as the zeros. How many of them are there going to be? Should say there's going to be 4 of them. So to find them, we're going to set the function equal to 0. That's why they get called the zeros. And now let's factor this. So I want to multiply to 1 and add to -2. So -1 and -1. I'm going to rewrite this one just to show you what happens. (x squared (x squared) plus 1. So I rewrote the middle with my 2 -1s. Group. So it looks like I get x squared minus 1, x squared minus 1. Now, if we really wanted to, we could factor each of those again because both of them are the difference of squares. If I set each one equal to 0, it looks like I get a 0 of -1 with a multiplicity of 2 and a 0 of 1 with a multiplicity of 2. So I do have 4 zeros. It's just that they were repeated. The next thing that would be helpful to find is the y-intercept. So remember, to find the y-intercept, we're going to put 0 in for the x's. And if I do that simplifying, my y-intercept is 1. And finally, one other thing that might be helpful when we make this graph, would this graph be considered as even, odd, or neither? Well, let's look at it. I have an exponent of 4 and an exponent of 2, and technically this last guy has an exponent of 0. Since all the exponents are even, remember we called this even. Well, how does that help me with the graph? If it was an even function, it had y-axis symmetry. So that tells me it better be a mirror image over the y-axis or something's wrong. All right, let's see if we can get this visual now. We did all the hard stuff. Now it should be the easy part. So what I tell people, let's first plot our zeros. So we had an x-intercept, a 0 at -1, and we had one at 1. Great. The next thing, let's put our end behavior on. So I know the two ends are doing this. Right? We said it's going up on either end. Let's plot, do we have a y-intercept? Yes, our y-intercept was at 1. And now we have to decide with these x-intercepts, am I going to cross through them or am I just going to touch them and turn around? Well, the x-intercept at -1 had an even multiplicity. If it has an even multiplicity, it's going to touch it, but then turn around, not actually cross through. Same thing for the other one. And there's our graph. Let's check. How many turning points does this thing have? Well, it has 3. It turned around 3 times, and that makes sense because n was 4, and remember the turning points is always 1 less. So there's my graph. Also, here's the y-axis. See how it has y-axis symmetry. It's the same on either side. All this stuff starts tying together nicely. One more. So this one I want to graph. Let's first do the end behavior. So now this one, we're going to have to kind of do our multiplying here. So if I took -2 times x, but then times another x because it's squared, I would have -2x squared, but then times another x. So my leading term would actually be a -2x cubed if it was all multiplied together. So because my exponent is odd, and the number out front, the leading coefficient, is negative, my ends are going to be going opposite ways. Okay, the next thing, x-intercepts. So also known as the zeros. How many of them are there going to be? There's going to be 3 of them because that's my degree, the highest exponent. So I'm going to set it equal to 0. And good news, they've already factored it for us. So let's set each piece equal to 0. And solve. Well, this first one, notice there's no x, there's no variables, so that's garbage. I'm not going to get anything out of that. The next one, I will tell you we get 1 with a multiplicity of 2. I got that answer twice. And this one, if I subtract 2, I'd get -2, but I'd only have that answer once. So I do have my 3 zeros. And then the third guy, I have a y-intercept. So if I put 0 in for the x's, -2, so we'd have -1 squared, which is 1, and then 2. So -2 times 1 times 2. I have a y-intercept of -4. And finally, would this be even, odd, or neither? It might be a little bit hard to see it on this one, especially since it's not multiplied out all the way. So let's hold up on that and see if we can get it without knowing that. So let's plot our zeros. So I had an x-intercept or a 0 at -2, and I also had it at 1. Let's also plot our y-intercept. Okay. Let's do the end behavior. So we said the ends were going opposite ways, so I know the left side is doing this, and the right side is going to do this. And now we just need to figure out the middle. So this first 0, -2, I only got it 1 time, an odd number of times. So that means I'm going to cross through it. I'm crossing through it. The x-intercept of 1, I got an even number of times, so I'm going to touch it and turn around. The last thing is I'm not quite sure what's going to happen in between these. Do they connect here or do they not? If you're not sure, You can pick an additional point. So like if I made myself a little chart and I want to know if x is -1, what happens? Well, if you plug -1 into the function, -2, so -1 minus 1 is -2 squared is 4. -1 plus 2 is 1. I get -8 out. I'm going to go ahead and plot -1, -8. So what that does, it gives me just a little bit better idea of the graph, that it's going to actually head all the way down. So you can always pick additional points if you want your graph to be more exact. How many times did this graph turn around? It had 2 turning points, and that makes sense because our highest exponent was 3, and it's 1 less. We can also go back to number 4 and see that, whoops, this graph does not have any type of symmetry, so it turns out this would be neither even or odd. It doesn't have symmetry, so that wouldn't have helped us anyway to graph it.